Um, Thank you. So first of all, I would like to thank the organizer for giving me the opportunity to talk at this wonderful event to celebrate the works of Yale, Lisa, and Jonathan. This is a wonderful community. So everyone knows, anyone knows them, knows that they are extremely kind, and their mathematics is very influential for all of us. As a student of Lisa, I've benefited a lot from this. So this is a photo in 2004 in AIM, August 16, so almost 20 years ago. So many of the people at that workshop were here or was here at this conference as well. That's Megumi. I have a story about Lisa. So she's my inspiration. So she's extremely kind to all her students. And I remember that towards the later year of my PhD, I was really stressed about my thesis. And she had a sabbatical and was invited to go to Princeton for that. But she declined. She stayed because I was just really anxious about my thesis. So Lisa, thank you for everything. Okay, so the plan of the talk is I will have a quick review about moduli space of flat connections in general. So we will look at flat K connections where K is compact. And then we will look at flat G connection where G is the complexified group. So in there, we will also just look at one of those evolutions which comes from the non-orientable surface, so induces a deck transformation, and we will look at some of the geometry of it. And then we will look at the new example, which comes from the TD-star-Toda equations. So the first two, those moduli spaces are smooth connections. So including the part which you have just boundary components, so that would correspond to just pole of order 1. But then for the meromorphic connection part, this is honest singular things, so the pole of order higher than 1. So you will see that over here, the involutions actually are embedded in equations. So it's slightly different. Oh, sorry, I forgot to stop my stopwatch. Okay, so we will start from reviewing some of those moduli spaces. So we start with a flat K connection. So K is compact Lie group, so it's known as the Thiel-Bott situation. So you have a Riemann surface of genus L, compact Lie group, and principal K bundles and adjoint bundles. So you consider the space of all flat connections, all connections to start with. So it's a fine space, and the underlying vector space is the one form where the value is in the adjoint bundle, and you have the gauge group acting on that. So the gauge group can be viewed as all the smooth maps going from the surface into the K bundles. So in Thiel-Bott's paper, they consider this Yang-Mills functional on the space of connections. So you integrate it over the curvature. So basically it's the L2 norm square of that. And so from they applied this Moore series on this space of connections. They have this infinite dimensional Moore stratification, and they consider the critical sets of this functional. So the equations for being critical for this functional is that dA star FA is equals to 0. So that's known as the Yang-Mills functional. And the critical points are called Yang-Mills connections by them. And so because it's the square of the L2 norm, so the value is non-negative. So flat ones are naturally the minima for the Yang-Mills functional if they exist. And when it doesn't exist, then you just consider the minima ones. So it's, you always have something that you can look at, and you have the gauge actions, and then you look at the moduli space by this gauge transformation. So that's the moduli space that we would be looking at. And so for each fixed P, you would have a moduli space. Now, if you collect all of them, so you can consider all the different principal bundles over the surface. So that's on this, on this side. So you would have all the principal bundles, and then you look at the moduli space as a whole. And then on the right-hand side, you would have the character variety, which first showed up in Bill's talk yesterday. So the natural map is going from the connection to its holonomy. So the detail of this can be found in Goldman's and Melson's paper. So there are many advantages of looking at the character variety. So one of them is the way to count the dimension. So because over here it's infinite dimensional quotient. So here you would have a finite quotient, and then the way to compute the dimension is quite nice. So at least on the smooth part, so this is usually singular, but on the smooth part, the dimension is 2L minus 2 times the dimension of K plus 2 times the dimension of the center. So if the G is semi-simple, then it's just 2L minus 2 times dimension of K. So this light purple part is about the non-orientable moduli space we will see later. So the dimension is also easy to compute. So it's just H minus 2 times the dimension of K plus the dimension of the center. So the H represents the number of the RP2. Okay, so we will see that later. So I will like to recall some of the results in the moduli space. So there are many, many, many results. So I will just only recall some of them. So the first one is about the symplectic structure on the moduli space. So the first one is the infinite dimensional quotient by Atiyah-Butt. So as we were looking at this space of connection, it's an infinite dimensional space. It's affine, and then it has a symplectic structure. So that is the symplectic structure over here. You integrate it over alpha with beta. And the gauge action is Hamiltonian with a moment map, which is by sending the connection to its curvature twofold. So as you can see easily that this is just symplectic reduction at 0, even though this is infinite dimensional quotient. So there were a lot of work being done in the finite dimensional construction. For instance, these are all very influential papers. So Goldman has the symplectic natures of fundamental groups of surfaces. Yale has this papers on the algebraic proof of the symplectic structure of moduli space. Lisa extended moduli space of flat connections. Alan Weinstein, the symplectic structure of moduli space, and AIM's Lie group values moment maps. So these are the finite dimensional constructions. And there are a lot of cohomology results and geometry on the moduli space as well. So you have a different way of looking at the moduli space. So this is the definition that I gave was just from the principal bundles point of view. But of course, you can relate that to the holomorphic side, and then you can consider the holomorphic structures, and you can consider the stability conditions on that side, and then you would have the algebraic version of the moduli space, and then you can study that from algebraic geometry, and then also because of the representation, you have another theoretic way of studying it. So those are results over there as well. And so this moduli space's problem has many important impact. For instance, the Atiyah-Butt's paper where they use this Morse series, so they have this equivariant perfect Morse certification, which influence the Kerwin surjectivity, which basically just says that the total space has this surjective map onto the lowest stratum. And also, the moduli space provides many important examples for new theories. For instance, in Aka's talk on Monday, so he mentioned that there you can look at the new examples, the moduli spaces as examples for the new theories. And also there is the stability problems, which is known as the Kobayashi-Hitchin correspondence, which talks about the differential geometry side with the algebraic geometry side. So you, on the differential geometry side, you can look at the flow. So basically you want to look at the minima of that flow. So that's the differential geometry side. You look at the metric of it. And then on the algebraic side, you want to make sense of some kind of stability conditions. So there should be some kind of relations between the two. So that's the Kobayashi-Hitchin correspondence. So, and there are many more, so that's the orientable version. And now if we look at a non-orientable surface, so H is the number of the connected sound of RP2. So of course, the principal bundle still makes sense. And you can look at the orientable double cover. So the genus is just, the relation is very simple, is L equals to H minus 1. And you look at the pullback bundle. So throughout this paper, throughout this slides, if I have this tilde, that usually means the pullback to the double cover. And so the deck transformation the Dex transformation, tau, induces the involutions on the space of connections and also on the space of gauge group. So you can have on one side, you have the principal bundle, you have the flat connection, you can look at the gauge transformation on that, so that gives you a moduli space of flat connections over non-orientable surface. And on the other side, you can look at the moduli space of its double cover, and then you can compare these two. So they have a non-trivial relation between them. So John worked with Melissa Liu a while back. It says that this moduli space of flat connections over non-orientable surface, it's a totally real and Lagrangian inside of the moduli space of its double cover. And if you compare the fixed point set on the double cover, so this is considered the representation. So character variety as a whole, so you consider all the possible ones over the non-orientable surface. And here is on the double cover. So again, you consider all the possible principal bundle. And you look at the fixed point set, then the map going in is a covering map. And it's not surjective. It will only maps to the part which corresponds to the trivial bundle. So recall that earlier we mentioned the character variety will count all the possible principal bundles, but the one which is on the image of this map is only the one which corresponds to the trivial bundle. So the thing is that for the principal bundle over non-orientable surface, all the bundles have flat structure. But this is not true in general for the Riemann surface. And then if you look at the pullback, then the pullback on the double cover will always be trivial, topologically trivial. So that can be checked by using the obstruction. And also, you can look at the Morse stratification. So it's a natural question. So you look at the Morse stratification for the space of connections. And then so you basically use the original stratification for the double cover that Atiabat did. So that's what this comments is about. And then you intersect it with a fixed point set. And because the tau may not preserve the strata, so actually not all strata survive, so some will disappear. And so we can give a algebraic description of those representations, so those critical set as well. We called it a super central extension. So in originally Atiabat's paper, they call that a central extension. So you have a nice description. The super, we put it here just because it encoded Z2 for non-orientable surface. So that's the compact situation. So if we look at the complex one, you start with the Young-Mills equation. So that's still K. Okay, so that's still K. So that's the equation that we just saw, right? And then so if the base space, now we look at R4, then both self-dual and anti-self-dual satisfy these equations. And so Hitchin studied the self-dual equations on R4, and then he applied the dimension reduction. So now it becomes a two-dimensional equation. Oh, so he started from consider this equation on R4. Yeah. And then he applied dimension reduction to get R2, yes, to get a Riemann surface. And so Hitchin equations, so the one that I'm describing is one version of it. So you might see the different version, like using Higgs bundles, but I'm using this differential geometry version of it. So you consider this pair on the tangent bundle of the space of connections. So A psi is a pair, and this is the Hitchin equation. So it's written as this three equations. So the gauge group again act on this tangent bundles. So as you can see on the connection part, it's the same as before. So now you just have an extra part, which is the psi. So Hitchin moduli space can be defined as solutions to these equations and modeled by the gauge group. So this is using compact gauge group. But you can see that if we look at this, then the connection A has this relation, which means that they may not be flat. If psi is not 0, then it is not flat. So the way to change that, this is Donaldson's work. So the way to change that is by looking at the complexified group. So you would have the G bundle. So G is the complexified group of K. So if A psi, so if this pair is a solution to Hitchin equation, then when you do this combination, so A minus I psi, this is a typo, so this is PC. Then this is a flat connections. And moreover, if you look at the complex gauge group, because now we are looking at the complexified principal bundle, and you look at the complex gauge group, then Donaldson Collette shows that the moduli space, so the Hitchin moduli space, is homomorphic to the de Rham moduli space, meaning that you look at the moduli space of flat connections. But just as mentioned by Bell yesterday, when you go into the complex side, the orbit may not be closed. So you take the reductive ones, then it will have the closed orbit. So this homomorphisms is that you start with, like, think of the space as flat connections. So you are inside of the flat connections, and your orbit is the complex gauge, right? And then so if you start with a reductive one, then when you flow inside of the complex gauge orbit, then you will hit the solutions to Hitchin equations. And it's not unique, but it will be unique up to the compact gauge transformation. So that's this homomorphism means. Okay. So you have this nice homomorphisms between the Hitchin moduli space and the flat connections, which is the G group. I'm checking the time. So there is this nice hyperkähler structures on the moduli space. I will go a bit faster. So you have this I1, I2, I3, and the reason that I order them in this way is because I want this I2 to survive under our involution. So you have this three complex structure and the corresponding symplectic forms and the corresponding moment map. So this nice moment map, as you see, are exactly the equation that we saw earlier. So the moduli space of Hitchin equations can be viewed as just the hyperkähler quotient for all these three. So you take the hyperkähler quotients at 0, then that gives you the Hitchin moduli space. So that have a nice hyperkähler structure induced on the moduli space. And this is just to mention briefly that you can also do this two-part, and you start with a holomorphic symplectic form, and using the mu2, you also have this quotient. So this mu2 will be the one that survived under this involution. So consider a non-orientable surface, and we can also make sense of Hn equation, and you can define the Hn moduli space, and Dirac transformation on the double cover also induces this involution on the tangent bundle on the space of complexified connections and gauge group and so on. So joint work with Wilken and Wu, we show that Donaldson and Collette also hold. So you also have this homomorphisms between the Hn moduli space and the flat connection moduli space. And now nicely is that you have a symplectic quotient. So this moduli space now can be obtained as a symplectic quotient, and that moment map is this mu2, so that will survive under the involution. And you would have, moreover, a Kähler structure on this. So this is an example of the ABA branes in Kapustin-Witten's paper. So I'm going a bit quick because the main thing for me is that I would like to introduce different kind of geometry that show up in the fixed point set of involutions for the moduli space. So now we have seen two different types. One is Lagrangian, and then this one is symplectic. But if you look at the I1, of course, that's still Lagrangian. Okay, so that's this two part. So now we will look at this new examples. So it's TT star Toda equations. So TT star was first introduced by Chakotay-Vafa in 91's paper. And Dubrovin made a mathematical framework for that in 93's paper. So that's where we are coming at. So we consider particularly the Toda type. So this star is the Toda equations. This is the Toda equations. And with this condition, so this is where the TT star comes in. So you have periodic, and it's radial, so it's only depending on the length, because this is on C. See, this is on C. So it's only depending on the length to 0, not the angle. Okay. And it's anti-symmetry. So Wi plus Wm minus I equals to 0. Yes?
Sorry, all these conditions together?
Yes, yes, yes. So you consider Toda equation, and then you impose all those equations. And then that gives you the TT star Toda equation. So if you look at the simplest case, which is n plus 1 equals to 2. So that's the simplest case. So then W0 plus W1 is 0. So you just have one of them, just one equations. And that is the Sine-Golden equation. So it's something no. And this was discussed in great detail in Chakotay-Vafa's paper in this case. And guessed its Ling. They solved this PDE. So this is PDE with this condition. They solved this PDE for lower rank in 2015 and general rank in 2023. So solved this means that they have the solutions for the global solutions, and as well as smooth near 0 and infinity separately. So that's the result that they had. So in Dubrovin's mathematical framework, he showed that those equations that we saw in the previous page, they correspond to a family of meromorphic connections on CP1 with structure group is SLN plus 1C. So this is the AN type, which has the isomonodromic property. So which means that within this family, so this is T family, so within this family, as you move, the monodromy data remains the same. So we will look at what monodromy data we are talking about, but monodromy data remains the same. So that's the isomonodromic property for this meromorphic family. So in local coordinate, so zeta is our coordinate, then this meromorphic connections can be written as such. So we can see this is 1 over Z2, and capital W is this matrix, which on the diagonal part it's 0, and other than those exponential, everything else is also 0. And the second term is a diagonal matrix. So on the diagonal part, they are the W, which is the function we saw earlier as well. So X is just, we just change the notation. So because the absolute values of T representing the family, so that's the parameter. So you have a family of meromorphic connections where in here, these are functions of zeta and your parameter X. So you have this too. So that gives you this family of meromorphic connections. And so the flatness of these meromorphic connections corresponds to meromorphic ODE. So you look at the D minus alpha hat transpose, then you end up with this nice meromorphic ODE. Otherwise, you will have a minus sign. So that's why you do the transpose. So this is the meromorphic ODE. So this is where we are going at. And you see that it has a pole of order 2 at zeta equals to 0 and pole of order 2 at zeta equals to infinity. So it's just CP2 will have 2 poles of order 2. So now it goes to the flat connections having the algebraic data being the holonomy. So this is Riemann-Hilbert correspondence. For the meromorphic connections, you have the monodromy data. So what are the monodromy data that we are talking about here with these meromorphic connections? They are the Stokes matrices, and you have the formal monodromy, and you have the connection matrices. And if your base is not just CP1, but rather like a Riemann surface in general, then of course you have all these other holonomies as well. So it's just a combine of all of them. So I will very briefly explain what those Stokes and connection matrices are, but I will not go into detail, but if you're interested, I can explain to you later. So for the meromorphic ODE that we saw on 2 pages before, it has a unique normalized formal solutions. So when the order of the pole is higher than 1, then this formal solutions no longer converge. So it's just a formal solutions, it doesn't converge. But you would have, you can consider those Stokes sectors corresponding to that formal solutions. And on this pole 0, so you have those Stokes sectors, and they are defined using the singular direction. So theta I are the singular directions, and singular direction are determined by the system. So as an example, you can see this is a 4x4 case. So if this is particularly nice because for our system, the singular direction actually are evenly distributed. So it's evenly distributed like that. And then if you number them counterclockwise, and then say you start the first one here, then omega 1 is by going backwards pi over 2. So this pi over 2 is because pole of order 2. So this is going back here. And then on this side is the previous singular direction going forward pi over 2. So you have a sector, which is omega 1 like this. So you define your sectors. So first you have singular direction, then you define sectors accordingly. So even though the formal solutions does not converge on the whole sector, on the whole region, C star, but on the smaller ones, so on the sectors, correct ones, you will have unique solutions. So not too big, not too small. You will have unique solutions, so those are holomorphic solutions. And they have some relations to the formal solutions, which is that as you approach this to 0, the asymptotic is the formal solutions. And as we were saying, because they are unique, right? So what about the part where your sector has overlapping? That means that the solutions can only be differ by constant matrix. So that's the Stokes. Okay? So the Stokes are defined as the difference between the holomorphic solutions. So you have SK and Stokes factors and so on. So that's the data at 0. So at infinity, of course, you can have this whole set of data as well. And then the connection matrices are the information which connect the 2 poles. So on one side, you have the 0, and on the other side, you have the infinity. So you have the holomorphic solutions, and you do the analytic continuations, then there is a difference between them. That's the connection matrices. And you can see that it involves a lot of choice, right? So it depends on where you start and so on. And then so the symmetry that we saw on the first page of the section 3, it will give you symmetry on the connections forms. So these are the connection forms that you have. So you have the cyclic symmetry, which comes from Toda. And you have the anti-symmetry, theta reality, and C reality. So for C reality, you can see that this zeta will relate informations from 0 to infinity. And all those notations are Lie algebra automorphisms on the Lie algebra. So you have tau, you have sigma, and theta, and C. So they look quite simple in the face of this connections. So they are just conjugating by constant matrices, and they might have a bar, they might have a transpose, but it is not too bad. So the cyclic symmetries, the Toda conditions, so the effect on the Stokes factors is that it will tells you that all the other Stokes factors can be obtained from 2 consecutive ones. So you just need 2 consecutive ones, and you can generate everything else. That's the Toda. And also because the formal monodromy is trivial here. So in GIL's paper, it's a computational result, but we will see a Lie theoretic reason why this is true in the later slides. So that's the holonomy, right? So you have psi 1, so that's one of the holomorphic solutions. If you go around, then the difference is your holonomy. So that's the first Stoke, second Stoke, and formal monodromy. And because it's trivial, so that's just S1 and S2. And then we were saying that S being the Stoke matrices is just the product of all the Stoke factors, QK. So SK can be decomposed into the product of them. And then so because of the symmetry, it becomes just this. So you just have the first one, then the second one, and the pi, which is a constant matrix. We will also see why this exists, to the power of n+1. So it's very clean, it's very nice. And moreover, the C reality relates the Q at infinity to 0. So it's enough to just consider the one at 0. So also the cyclic symmetries on the connection matrices implies that all the EKs are determined by the first one and QK. So that will generate all the EK that you want. And so for the monodromic data's point of view, the building blocks are Q1 and then Q1 plus 1 over n+1, so the 2 consecutive ones, and then E1. So that's the building block that will generate all the monodromy data that we want. So our goal is to understand the geometry of all local solutions. So we will be focusing on this. And so notice that in GIL, they consider global and solutions, and smooth near 0 or infinity solutions is because they are interested in the PDE result. But for us, we would like to have geometry. So if you want to have geometry, we'll see hopefully in the last page, you will see a picture of this space of all local solutions. So you will see that if you want to have a geometry, like a nice geometric space, you have to extend, you have to allow the things that you want to consider. So we want to consider all the local solutions. Okay, so we will first review some of the results on the Stokes factor and singular directions. So this is generalized to all complex simple G. So the original TT star is on AN type. So we generalize to all the complex simple G. So first of all, it's about the formal monodromy. So as we saw earlier, that in the AN type, the formal monodromy is identity. And the reason is precisely because that in the coefficient, so if you remember, you have 3 terms in the equation. So the first 2 terms determine the formal monodromy. And the coefficient that they lies in are in 2 different catons. And the solutions is by projecting one to the other katon. And then because they are katon in opposition, so the projection is 0. So that's on the Lie algebra side. So it becomes identity for all possible ones. All the different groups, they will vanish as well. And secondly are the singular directions. So normally singular directions are obtained by looking at the differential equations. But in the case here, because of the toda, actually, so the singular directions can be identified with the rays in the Coxeter plane. So for each different group, you have a Coxeter plane, so where you have the dot representing the roots, right? And then you can look at the rays going from the center out. So that's give you all those different rays, and then they identify precisely with the singular direction for this system. And because of Bosch's result telling you that the Stokes vector relating the roots to the singular directions, so as we were saying, each singular directions corresponds to a Stokes vector, right? That representing that when your solutions go across, it differs by a constant. So those things, those matrices are given by these roots. And the Coxeter element, gamma, so it depends on how you choose your theta one, so which one is your first one. So that Coxeter element will act on the Stokes vector by rotating the singular direction by 2. So it just goes from 1 to 3 to 5, and then 2 to 4 to 6, which means you really need 2. So that's the theoretic reason behind the computational result. You only need 2 consecutive ones to get all the Stokes. So inspired by this 2 result, we defined this space of all possible Stokes. So that's the curly m n plus 1. So this is the product of the exponential of the root space of alpha. So all the roots on the first singular directions. And here is all the roots on the second singular directions. And then you look at the root spaces of them. And then the exponential, and then you take the product. And then you have this pi. So this pi is the Coxeter element, the group representation of that. Okay. So for instance, our QQ pi that we saw earlier, so this naturally lies in here because the way we defined it. So this element, so combining QQ pi as one element m, that will give us back all the Stokes that we want, S1 and S2, as you can see in a very simple form. So this really encode all the information that we need. So we call it possible Stokes because not all of them corresponds to the solutions. So not all of them are actual Stokes that we want, but it's a bigger space. So our result is that we show this is in fact a Steinberg cross-section. So you can move them, all those root spaces, to the Steinberg cross-sections. So it's a cross-section on the conjugacy classes of regular elements. So this is very useful later on to understand the geometry of it. So the new result that we have is because we want to study this S local, right? So we want to know what S local is. If we just use the E1 that we mentioned, then it doesn't have very nice symmetry. So we modified it a little bit. And now we have this commuting property. So now you have the M, and then you have the E, and then they will commute. So now we can define this S local. So S local is defined as this pair E and M. So E is in G, and then M is n plus 1, and they commute, and it imposes this theta and sigma. So I need to justify this later on. So they are induced by the theta and sigma on the connection. So now they are on the monodromy data, and especially the modified monodromy data. But their action doesn't look as simple as before. So as before, in the many slides before, the theta and sigma are conjugating by constant matrices, but now it's not. So yeah, just a remark about this space. So this is in fact a universal centralizer at the group level. It was mentioned the Lie algebra level on Monday. So this is the group level. So what the form looks like. So sigma and theta on the connection E and Stokes M. So this is conjugating. So E and M has to do something themselves, and then they conjugate it by this A and M and B and M. So they are functions depending on M and N. So it's not constant. It has to do something. And for example, if you look at N even, then the AN is the transpose of the first Stoke. And if N is odd, then the BN looks like this. So it's even more complicated. So it's the Q, but it is Q at N over N plus 1. And you have a C tilde, which is a constant matrix. So of course, they are all coming from the M. So from M, you can reconstruct all those things. So they are related to M, and then they are related to N as well. So you have all this maps. So that the problem is that if you look at them, then they are not obvious to be involutions. Because what happened is that when you map it once, and then when you are applying it again, then the point moves. So the function AN and BN that you want to conjugate no longer are the same. And so it's not even clear that the space will be preserved by those two maps. So we have to justify that. And also we have to look at this, how you deal with this kind of maps on the space where they look so bad. So luckily, the groupoid comes to the rescue, like in Rear's talk as well. So in fact, groupoid is the right framework to study this space, precisely because of this seemingly not very nice behavior of the involution or the map. And we are grateful for Eckhart, who suggests us to take this point of view. So the result that we have is that if we look at the space of solutions, local solutions, then it's a groupoid over the unit is the Stokes information. So M, so here are all the Stokes matrices. Well, to be precise, it's the M, so the QQ pi, but the Stokes informations up to this fixed point set. So these are real symplectic groupoid. So I will make sense what real means, but it's a Lie groupoid, and it has a symplectic structure on it. And the space of all this Stokes informations is Poisson naturally because of this. Yeah, so it's really nice. Pardon me? Yes, yes, yes. So we will see the approach. So we start from the AMM groupoid. So it's a quasi-symplectic groupoid with this 3-phone and 2-phone. And if you look at this universal centralizer, we denoted by Z, then that's a Lie groupoid over this M plus 1, the space of possible Stokes. And the inclusions are Lie groupoid morphisms. So you can pull back the 2-phone, and you can check that it's a symplectic groupoid. So it's satisfied the multiplicative, it's closed, and it's non-degenerate. And the power of the groupoid comes in when you have to check this. If you want to check it on the whole space, it's really difficult. But when you only have to check it on the unit, that made it possible, because you have a very nice decomposition on the unit of the tangent space. So you were able to do that on the unit. Oh, yeah, so Balibama also showed that the universal centralizer is symplectic with a different approach. So I will jump this part, but basically here we are talking about how we show that it's involution, how do you make sense, and theta and sigma are commuting Lie groupoid morphisms. And notice that they are not, the commuting part is non-trivial because of the AN and BN are defined depending on the point. So once you change the order, they look different. They are different things. You have to really use that it is Steinberg cross-section in order to do many of the things. Okay, so because this is on the SLn+1c, so in fact, those omegas are holomorphic symplectic form. And so if you look at the sigma involutions, then the sigma involutions are symplectic. So the sigma involutions are symplectic. And so you look at, you can check that the fixed point set is still a Lie groupoid, and this form is a symplectic groupoid. So multiplicative and all those things work. So this is the inclusions from the fixed point set into Z. So one remark is open dense because the fibers are not always S connected. So we know that if you check something to be equal on the base, on the unit, you need the fiber, S fiber, to be connected in order to match them. So you only have open dense. So you have to, like, there is some subtlety, but it works. And secondly, if you look at the theta involutions, then it's not symplectic, it's something like this. So it's minus of the bar. So if you write this holomorphic symplectic form as omega 1 plus I omega 2, then because it's like this, so the one that survived is the omega 2. So that's why we call it real symplectic, because it's one of this form. And both omega 1 and omega 2, they are multiplicative and so on. So it's honest Lie groupoid, symplectic Lie groupoid. So with the fixed point set over here, with the fixed point set over here, with the pullback of the omega 2, you have a real symplectic groupoid. So that is the space that we want, right? So this is the S local. This is the space of Stokes informations. So as a justification, I will end with this picture. So it's, again, a full whole sphere that shows up yesterday as well, but it might be a different one, I'm not sure. So here is a result by Guest and Hertling. So it's a situation when you consider n+1 equals to 2. So it's full whole sphere, it goes to infinity, And so this is considered all the local solutions, then you have this very nice thing. You can decompose it into 14 different strata corresponding to different type of solutions that you actually get. And if you write them, so this is a nice choice. So you have to make a good choice of the parameters inside of the space in order to have this. So with this nice choice, you will have this full whole sphere and the different stratum representing different things. So some of them are global solutions. For instance, these compact ones are global solutions. And then you have smooth near zero, smooth near infinity, and local solutions are everything. So you have a nice geometry. So that's why we want to consider the bigger space. So happy birthday to Lisa and Jonathan. Great.